All right, everyone, welcome back to our April PCast. Before we get started, we'll do just a couple of news items. So Prima will be at the Summer AAS in Pasadena, California in June. We'll have a special session on Monday, June 15th in the afternoon from 2 to 3:30. This is going to feature a lot of folks from the team just giving some updates on PRIMA as a general observer facility, and then a number of talks from folks in the community. And then we're also going to have time at the end of the session, just a little bit of time to meet and greet and chat with the team. Since being in Pasadena, both JPL and IPAC are planning to have strong presences there. Today's talk is actually the first of 3 upcoming talks on PRIMA PI science. So in May, in about a month, we're going to hear from Andrea Benzatti, who will be talking about the disks case. And then in August, we're going to hear from Irene Shivai, who will be talking about the case for dust and metallicity and polycyclic aromatic hydrocarbons. But today, of course, we're all here to hear from Jed McKinney. So he's going to be talking about the PRIMA science case for supermassive black hole and galaxy coevolution. And Jed, of course, as with the other 3 speakers, is one of our PRIMA affiliates as part of the science team.
Cool, thank you, Betsy. So I'm going to take it away now. Great. So hopefully y'all can see my screen. Please speak out if you can, because I can't see you anymore.
Looks great.
Okay, awesome. Thank you. Yeah, really excited to be talking about the PRIMA PI science case for supermassive black hole and galaxy coevolution. Thanks for the great intro, Betsy. So yeah, my name's Jed. I'm a Hubble Fellow at UT Austin. It was really exciting to join the PRIMA team as a science affiliate, and I've also been working as the Galaxy Evolution Working Group co-lead alongside Irene Shivai, which has been really rewarding to engage with the PRIMA community along that axis. I mean, we did a lot of support and coordination for the Go Book Volume 2, and it was just really awesome to help facilitate all the fantastic science cases that people were ideating around for what PRIMA could do for them. But I'm not going to be talking about that today. I'm going to be talking about the PI science, of course. So yeah, I'm just going to dive right in. And I'm going to kind of zoom out really big here and just make the point that PRIMA really stands atop the shoulders of giants in some way, and it builds on a really rich legacy of infrared missions, of course, many of those being in space, needing to get out of the atmosphere, but also things like Sophia as well. So it's really exciting to be kind of like leveraging all we've learned from these past missions, dating back, decades, to continue to push into the discovery space that's really uniquely enabled by infrared astrophysics. And I know, and many people are on this call probably have a lot of experience observing the universe in the infrared, but just to give folks maybe who haven't worked so long at these wavelengths a really visceral sense for why we need to build telescopes that operate at long wavelengths. I love to start most of my talks actually by showing this graphic. So this is Barnard 68. It's a molecular cloud in the Milky Way. Some of you might have worked on science with this target. But it was back in the 1800s that Agnes Clerk, the first woman inducted to the Royal Astronomical Society, speculated that clouds like Barnard 68 were actually not regions of space fully devoid of stars, but rather they were themselves obscuring bodies. And indeed, as we started to build instruments that pushed to slightly longer wavelengths outside of where our eyes normally operate, like in the near infrared, we start to be able to see through the obscuring material and reveal sort of like background stars, which I'm showing here. And then once our telescopes push to much longer wavelengths, that obscuring material, which we now know is gas and dust, is revealed in emission. And so it's really these infrared observations that reveal the full astrophysical scenario. This is just like one small molecular cloud, small by my standards as an extragalactic astronomer, but right, it's just one molecular cloud in the Milky Way. This kind of picture really holds on much larger scales all the way up to galaxies themselves. So here I'm showing the HST image of M64. You can see kind of older stars in this faint kind of yellowish glow. You can see newly forming stars in these knots of blue and purple. But I think the most striking thing about this image are these thick obscuring bands kind of in a ruddy red and brown. And this is, of course, the gas and dust in this galaxy obscuring starlight in much the same way. And when we observe a system like this at longer wavelengths, that material starts to light up in emission. So this is that same galaxy observed now with the mid-infrared instrument on JWST. And what was once obscuring starlight, we now see is lit up quite brightly. JWST, of course, has been fantastic for spatially resolving the infrared component of nearby galaxies. So I love showing photos like this from the FANGS and FEAST JWST teams that really resolve the infalling gas and dust onto the very hearts of galaxies themselves. We can also zoom. So right now we're zoomed into sort of the heart of the galaxy. If we step back out, Alberto has been using JWST, of course, to look at the infrared component of gas and dust that is being expelled from galaxies as part of their interaction with the larger environment. And so here in red, we're seeing dust molecules that traced the expulsion of gas as it outflows from the system. Of course, this being a key regulator of the processes that drive galaxy growth, and I'll be talking a little bit about this more later in this talk. We can also Webb has also given us these great abilities to look at systems that are growing. They're active supermassive black holes, zooming into the very hearts of those systems as well to reveal the obscured component. Cool. So I've been mostly talking about individual galaxies up to this point, but I'm going to take an even further step back to galaxy surveys. This is all motivating the fantastic work that PRIMA is going to do, that the PI science will touch on. But just to begin here, so this is the Hubble Deep Field. This image was taken in 95, 94. And revealing, thousands of galaxies reaching back far earlier into cosmic time than we had ever really probed. But just a year later, the same patch of the sky was observed in the submillimeter with the SCUBA instrument. So this is the SCUBA 850 micron image of the Hubble Deep Field. I think a few things pop out, right? For one thing, the infrared image of the universe looks vastly different than the optical one. And so just like we need sort of all wavelengths to capture the full characteristics of, say, a molecular cloud in the Milky Way, we need sort of that same thing to tell the story of galaxies across all of cosmic time. Which brings me to sort of the history that galaxies have written over the past 10 billion years or so. And so I want to kind of quickly summarize basically how galaxies have formed their stars and grown their central supermassive black holes over that time period. And so what I'm showing here is the star formation rate and density of the universe. So this is also as a function of redshift on the lower axis, or age of the universe, time since Big Bang, that's marked on the top axis. Right, so what this is doing is you kind of take some representative volume of the universe, you count up how many stars you find, your new star formation that you're finding, and you have to do this in the infrared with surveys at infrared wavelengths, which gives rise to the orange curve here. And then you can also look at the unobscured component of galaxy star formation with telescopes operating at shorter wavelengths, and that history is sketched in blue. And I think what you can kind of see very clearly is that for most of cosmic time, star formation is overwhelmingly embedded within clouds of gas and dust, meaning that it's heavily dust obscured. And to get an accurate handle, we have to build these infrared survey facilities that can chart that have charted that evolution. So this is the star formation of a component of galaxies. You can play the same game with the growth of supermassive black holes. So that's what I'm showing here. Redshift along the x-axis. So moving from on the far right earlier in cosmic times to the left being kind of present day. And this y-axis is the growth rate or the accretion rate density of supermassive black holes. Really playing the same game here, taking some representative volume of the universe, counting the accretion rate of all the black holes that you can find, doing this in the infrared to get that dust obscured component, and at shorter wavelengths for the unobscured component. And we see sort of the same story emerge, where that for most of cosmic time, just like stars, the supermassive black holes at the hearts of galaxies are growing heavily obscured by dust, and therefore we need these infrared facilities to capture that evolution. And just to kind of reiterate this point, right? Most of the history of the universe is dust obscured. Redshift can be a little misleading as it's not like a linear axis, of course, with cosmic time, but the shaded regions that I've drawn here out to about a redshift of 4, when we know that star formation and supermassive black hole growth both reach their peak. This is really like the last 10 billion years or so, and overwhelmingly dust obscured. And so we really need the infrared here. And this, of course, is one of the big motivations for building, or a part of the motivation for building an infrared or a far infrared probe like PRIMA. And so I'm going to, Betsy talked about some of the other speakers who will be talking in the weeks to come about the other PI surveys, the origins of planetary atmospheres, and the buildup of dust in metals. Today, I'm going to be talking about the evolution of galactic ecosystems from young galaxies through rapid growth to galaxies today. These three components make up about 25% of the telescope's time. The remainder of that will be spent on general observing, and so serving the community and whatever fantastic science ideas they have. I won't be getting that into all of that stuff today. I'll be really focusing on this one component of the PI surveys.
Yeah, before you get into it, we might have a talk from the audience. Johannes, did you have a question?
Yeah, actually, I had a quick one. Thanks. What do you mean in terms of the supermassive black holes when you say obscured? Is that obscured in the visible or obscured in the X-ray?
That's a really good question. So I'm mostly referring to optical obscuration through the absorption of dust, but certainly that translates to some degree to X-ray obscuration as well, as the toroid, the optical depth of the torus increases. But I'm also thinking about this not only as the AGN system itself being obscured, but also that system seeing the host galaxy, which we also know as you move towards earlier times plays an increasingly important role in obscuring both the stars in the system, but also the supermassive black hole too.
Right, I was only asking because, I mean, of course, people looked at and the difference, how many percent are obscured. Maybe it would be also interesting to have plots for X-ray versus infrared. So to see, even in the X-ray, it's still a significant number, or maybe not, right?
Yeah, absolutely. I have a plot later that comes from a paper that did like a real population analysis, and they include X-ray data as well. And so I'll touch on that point later, Johannes, and hopefully that satisfies your question. But thank you. So I'm just going to dive right into this survey. So this figure on the right is sort of a combination of the two figures that I was showing earlier, the star formation rate density and the black hole accretion rate density. And what I think pops out on this figure, right, is that both of those trends, chart the rise and fall of mass assembly, both for supermassive black holes and stars, respectively. They peak at around similar times, at around redshift 2, when the universe is clearly the most active in growing these black holes and growing stars and galaxies. We see a similar rise leading up to that peak epoch, and then sort of a gradual decline ever since. And we also know, so this figure on the left is a sketch of the relationship between the supermassive black hole mass in galaxies and the stellar mass of galaxies. And if you were to make this figure at, say, any given redshift, you're really seeing a snapshot of this formation history that's illustrated on the right. And we know that there's a general trend where the more massive black holes live in the more massive galaxies, but and clearly the similar shapes of these galaxy evolution trends, suggest some interplay between the formation of stars and the supermassive black holes. Certainly, these are some of the most energetic events that galaxies undergo. So it's quite natural to ask, well, how does supermassive black hole growth regulate star formation and vice versa? They're growing from the same gas, so in some sense it's a little bit of a zero-sum game. But the path that galaxies kind of take through this figure on the left, there's many different ways to basically produce the observed trends at redshift 0 between black hole mass and stellar mass. So here I'm showing, some various observations for the mass of a galaxy relative to its black hole mass, and you can see, sketched by some simulations, various scenarios that perhaps begin with higher initial black hole masses, undergo various modes of black hole growth suppression as star formation feedback becomes efficient, growing the galaxy relatively more than the black hole, or prolonged phases of higher accretion rates that help grow that black hole much quicker relative to the galaxy component. And simulations tend to track different paths through these parameter spaces as they kind of predict different models for how galaxies, grow their stars and black holes. JWST has been, pushing into the very early universe and helping us kind of understand perhaps some of the origins of black holes. And it's still far from solved. But what I want to highlight is, JWST's little red dots. These are, possible candidate supermassive black holes at very early times. On the right, I'm showing one of the higher redshift LRDs. I think the highest redshift one from Anthony Taylor's work earlier this year, sketching the mass of the black hole just like a few 100 million years into the history of the universe. And so if you were to take a lot of these black hole masses at face value, we might think that galaxies begin this trend with really overmassive black holes, and then the galaxy mass kind of lags behind and eventually catches up to, relatively in a relative sense, to produce the black hole to galaxy stellar mass ratio relation that we see in the local universe. But really, most of cosmic time is far off this figure that I'm showing to the right. And so this is really just like a brief snapshot of the earliest history of black hole growth, possibly. And there's really a lot to be done at lower redshifts to stitch this picture together. And so this is the same figure we saw before on the left, but now on the right, I'm just showing various simulations that all predict very different pathways for galaxies as they arrive on the local stellar mass to black hole mass relation. Some simulations predicting that black holes are growing, very rapidly and very efficiently relative to their host galaxies, and then other simulations finding the opposite, but perhaps they're seeded with slightly higher black hole masses. And I'm not going to really talk about that seeding scenario, but that, of course, is a very interesting connection to cosmology. But nevertheless, this is what we want to measure, observations of black hole accretion rates and star formation rates. And the key here is doing so in mass-selected samples as a function of redshift and getting the accretion rate and the star formation rate in the same galaxies, right? So everything up to this point, I've been talking about, censuses of star formation or censuses of supermassive black hole growth, but those are coming from disparate samples. And so naturally, they're not plugging in a one-to-one sense to study this coevolution of the most energetic, events that galaxies undergo. And that's why the mid-infrared, which PRIMA operates in out to the far infrared, really are really powerful for doing exactly that. They provide unique signatures of both the black hole accretion rate and the star formation rate. And this mid-infrared component shifts into the far IR as you push out to earlier times. And the key here is that we can do this for the same galaxies because actually, thanks to the obscuration, we're not plagued so much by the relative outshining that an AGN might do onto its host galaxy. So we can actually look at the same galaxy and pull out both the black hole accretion rate and the star formation rate tracers. So Alison Kirkpatrick did a ton of work on this. About a decade ago, and here you can just see a really nice example of, galaxies that are almost purely star forming in the infrared on the lower axis of this plot, and then the spectral energy distributions of galaxies that have almost, are almost entirely dominated by the growing of their supermassive black holes. And so you can see sort of the transition into those two embodies signatures of both, from a continuum perspective, certainly the rising power law of the dust obscured torus, but also these PAH signatures around rest 10 microns that are really efficient at tracing star formation in dust obscured galaxies. So I don't want to harp on this point too long, but why just to motivate why we do this in the infrared, you can certainly measure black hole accretion rates using rest optical or optical and UV spectra. There are diagnostics of star formation, of course, at those wavelengths. But some of the key things to keep in mind, one is that outshining issue that I mentioned. So this figure on the right, this is 3C273. Really bright quasar nearby, and you can see that folks have had some luck uncovering the host galaxy in this very bright object through coronagraphy, which is super cool, but still remains quite a big challenge, especially as you go to lower ratios of the quasar luminosity to the host galaxy light. And then kind of hearkening back to Johannes's question, right? This figure on the lower right here is showing the ratio of the torus luminosity to the bolometric luminosity from a very holistic study of galaxies of growing supermassive black holes across wavelengths. And the key takeaway here is that for basically the last 10 to 11 billion years, more than about 60% of AGN are in this dust-obscured, highly obscured phase, which makes the infrared really important for tracking that evolutionary history. JWST has pushed spectroscopically out to the sort of mid-infrared. I'm highlighting a little bit of my work right here with some JWST data. So this is from a spectroscopic sample we did with the low resolution spectrometer, which operates in about 5 to 10 microns. So not quite in the wavelength regime that PRIMA picks up, of course, slightly blue of that. These figures on the left show effectively pure star-forming galaxies. We can see some of these PAH lines, as well as other star formation rate indicators and cool diagnostics of the cold interstellar medium. These figures on the right, the figure on the right shows some of the highest, the strongest AGN in the sample. And you can see some of those have strong features, still indicating star formation, like the 3.3 micron PAH, as well, even on top of this rising power law from the dusty torus. And this gives us a handle on, these galaxies, both the star formation and the black hole growth, in a way like PRIMA will do, and I'll get to that in a second. My student Virginia Vanasek here at UT has measured the star formation rates of these galaxies out to AGN fractions of 100%. So in some of the most active and obscured systems we have, and she's found that those galaxies have a roughly equal star formation rates as ones with no growing at AGN, and we're still working on plugging that into this picture of black hole and star formation coevolution. So this has been really exciting to study. But I think the point that I really want to make is that this is prohibitively expensive for JWST to do it in statistical samples. This whole program was, about 50-ish hours with JWST to do, 30-ish galaxies. And this is where we really enter into the PRIMA revolution. So here I'm showing a simulated Primager 3-color image that Mathieu Betherman has created as a mock. And through these 3D hyperspectral surveys, every galaxy in this image, every point, it will have a full infrared spectral energy distribution where we can do this decomposition, right? So, if we look at a galaxy in blue with a growing black hole, we can see that rising torus, that hot dust component, whereas a pure star-forming galaxy in this survey would lack that really high mid-infrared continuum, but of course be lit up in the PAHs. Separating those two scenarios with previous telescopes and data sets like Spitzer sampling at 24 microns and IRAC imaging up to 8, right? That's actually been really challenging, which is why Primager is going to kind of blow open this whole area using the approximately R of 8 SED sampling all the way from 25 microns out to 200 or so. That's going to give us a fantastic constraint on the relative contribution from stars and black holes to the mid-infrared, which will then be translated into determining both the star formation rates and the black hole accretion rates for all of these galaxies in this image. The PHIRES, which is going to be able to spectroscopically support this analysis through follow-up of Neon-2 and O4 emission. And I'm showing an example spectrum here as well. Right, and the number of galaxies in these surveys is going to be really transformative, right? I mentioned that, Webb has been making inroads on this science, but in sort of small sample statistics. That's totally going to be blown open by PRIMA. So these deep and wide Primager surveys at the 1 square degree level and the 10 square degree level will yield full infrared SEDs for, approximately 60,000 galaxies down to L star. Out to redshifts of 8 in the brightest systems, 6 in sort of the tip of the iceberg or star forming galaxies, and then like normalish galaxies about 2.5. This is going to be folded in, of course, to the black hole galaxy and star formation PI science, but it's also going to enable tons of guest investigator science as well. So if you want to get like a real appreciation for all the fantastic things that the community has envisioned, go see the PRIMA Geo Science book volumes 1 and 2 for how people would utilize this data in really interesting and creative ways. Right, so what PRIMA is doing, though, on an individual galaxy basis and at slices in redshifts out to approximately redshift 2 to 3, is to measure the black hole accretion rates and star formation rates in these luminous infrared galaxies. Right, so basically tracking both, putting galaxies on this figure individually at slices in redshift to test these various growth modes of stars and black holes. This figure, again, is like a little cartoonified. I really like this one that the PRIMA team has mocked up. So here we're seeing the ratio of the accretion rate of supermassive black holes to the star formation rate of its host galaxy as a function of redshift. This figure is comparing two semi-analytic models, the Santa Cruz SAM and Spritz, and you can see that these predict different physical mechanisms that produce the local scaling relation between black holes and stars, a slow black hole growth model and a fast one as well. And PRIMA is going to be able to, by putting individual galaxies on this plot and in doing so in a statistical sense, being able to bin by redshift, really isolate the pathway that galaxies kind of go through to hit the present day. So this is going to be really fantastic. It's going to tell us how we get here, right? How we get to Webb's beautiful images of present day black holes. And it's something that I'm really excited about. In the last, 10-ish minutes of this talk, I'm going to step away from the, growth of supermassive black holes and stars and talk about something that's potentially regulating both processes. And I hinted about this earlier with some of Alberto's fantastic images of dust in the winds of nearby galaxies. But that is, of course, the role of outflows. And this is a big part of the evolution of galactic ecosystems PRIMA PI program as well. Of course, we know that galaxies are, vastly complex interplays between, the aforementioned growth of black holes and stars, but also feedback effects from their larger environments. This has been a really rapidly growing area of research, a really exciting one in recent years, as we're able to understand the connection between, its galaxy, a galaxy sitting in its own sort of area, and how that couples to the larger circumgalactic medium and its environment. And so also through the energy input into the gas of galaxies by both stars and black holes, outflows really could be the link between star formation and black hole accretion, as we see, gas that's funneled potentially into the cores of these galaxies, driven out, that is then able to be reaccreted onto the, on larger scales and drive star formation in the host. These models require winds that eject gas, which also help quench star formation and black hole formation. And by observing the velocities of these outflows and the mass outflow rates, we can better constrain those models of how galaxies interact with their larger environment. There's a note here too that the cool component, so the 10,000 Kelvin or below temperatures dominates the mass, and I'll illustrate that again shortly. Again, JWST is making inroads on some very select pointed observations, very bright galaxies. This is actually the most luminous galaxy in the universe that Andrew Vayner and Tanio Diaz-Santos have been studying recently with Webb. This is a beautiful near-spec IFU map on the left showing the relative velocity components across the image. And then I'm going to zoom in on some of the ionized gas tracers, O3, H alpha, carbon 4. And here you can see, outflow components extending up to 10,000s of kilometers per second. So, we're witnessing very extreme regulatory feedback from star formation and supermassive black holes. And this is at a galaxy at redshift 4.6, so very early on in the evolutionary history of galaxies. But the same point stands. It's prohibitively expensive for JWST to make statistical samples with exquisite data that looks like what I'm showing here. And harkening back to that point I made just a second ago, the neutral gas outflow rate, so the cold component of outflowing gas, is equal to or exceeds the ionized gas outflow rate. And so what PRIMA is going to do is it's going to study outflows through the OH line. So here I'm showing OH outflows from Herschel observations. Blue is, if you can kind of squint here, blue is the systemic velocity and the systemic component, and the green and magenta curves are the decomposed outflow components from these spectra. And from Sylvain Vailloux' work, we know that outflows are basically ubiquitous at high luminosities. And that's what I'm showing here on the right, which is the fraction of sources with outflows as measured by Herschel in this OH transition as a function of the total star-forming luminosity, but also the AGN luminosity as well. So as the luminosity of both of these components is increasing, we're seeing them drive these outflows in galaxies. And PRIMA is going to be fantastic at measuring outflows through this OH doublet. I'm showing an example PRIMA PHI-RES high resolution spectrum here on the left. And you can see this is a 84 microns of observation, redshift 1.5. There's also 60 to 80 micron handles as well. And through observations like this and decomposition of the systemic source profile as well as the outflow component, PRIMA will measure the outflow velocity and the mass. So that will translate to things like what I'm showing here on the right, which is the mass outflow rate as a function of the total infrared luminosity of a source that you're looking at. Here I'm showing one or two models from Illustrious TNG and also some Spritz populations, and the PI survey here will be able to put, approximately 25 galaxies each into redshift bins on this figure to help constrain these outflow models. Again, leading us to, understand the origins of, local systems and how we build local galaxies, and then also, seed the outflow environments that we can see in exquisite detail with Webb. So that's really all I have to talk about to y'all today. I'll let the other speakers coming up later this month and next to tell you about all the fantastic other PI survey components on the origins of planetary atmospheres and the buildup of dust and metals. But I just wanted to close with the fact that I really didn't talk at all about all the fantastic general observer and guest investigator potential that PRIMA enables. And so, the PI component of this telescope is fantastic, and it's going to really revolutionize our understanding, among other things, on the coevolution of stars and AGN. But if you're interested in hearing a whole slew of research topics, I encourage you to go check out the Geo books and investigate all the fantastic PRIMA science going on there. So thank you for listening. With that, I'll take some questions. Still can't see it.
Awesome. Yeah, thanks, Ted. Folks can go ahead and raise hands or speak up, and we can go back to slides as needed. JD, go ahead.
Hey, JD.
Hey, Jed. Hey, thanks for that. I mean, we have had our nose in this particular science case for so long. It's just really refreshing to see a fresh take on it. I'm very excited again about it. One thing that stood out to me, it's not really part of the PI case, but it's related. You showed a figure, just with the broad evolution of the density of star formation and the density of black hole accretion in the universe integrated. And it was interesting to me to see that the peaks had kind of aligned. As I recall, there used to be sort of a big debate about the delay between the peak density of star formation buildup and the peak density of black hole growth. Would you say that has sort of firmed up in recent times? Do you think PRIMA will have a role potentially through the guest investigator program to look at that?
Yeah, absolutely. So what, I'll share my screen again. Thanks for the question, JD. And we could talk about this for quite some time, I imagine. So the question being, the peaks of the star formation rate and the black hole accretion rate density, there's very interesting toy feedback models to invoke that would explain perhaps the early onset of star formation and AGN growth, and then when an AGN really kicks on, you start suppressing your star formation, which might change the times at which, statistically speaking, these trends kind of peak and shift relative to one another. I think PRIMA is going to be totally transformative here. I don't have a figure for it, but I'm going to call out some work done by a colleague of mine, Olivia Cooper. Olivia is a NSF fellow at CU Boulder, and she's looking at rest frame optical spectra of the types of galaxies that PRIMA is going to statistically survey, so infrared luminous galaxies out to redshifts of 2 to 3. And she is finding, in these canonically starbursting systems where we expect star formation rates, hundreds, thousands solar masses per year, she's finding really surprising diversity in the abundance of Balmer decrements, right? So the abundance of systems with really evolved stellar populations, and those that are really being caught at sort of a maximal starburst phase. And when you start to try to account for that systematically on figures like this one for star formation, the star formation rate density itself kind of slides around. One of the key unknowns here, really, that we're starting to fully appreciate is the degree to which the types of measurements that underpin the star formation curve here are reliable, namely infrared-based star formation rates. And what those suffer from are temperature degeneracies that Herschel was able to constrain for really the brightest systems, but most galaxies that we have, even out to redshift 2.5, still struggle from. And so PRIMA is going to be able to kind of pin down that infrared star formation in such to such degree of accuracy that I think we'll be able to kind of really tighten up where this peak truly is, and then assess relative to the black hole component.
Awesome. Thank you.
Awesome. Next up, we have a question from Matt.
I enjoyed that. I want to pick up on something you just said, which is the difficulty of comparing the obscured star formation, dust obscured, with the unobscured. And it's not really, like you said, a solved problem. You showed a graph that shows, okay, we already know that there's a lot more dust obscured than unobscured star formation. And I say, we really just don't know. For example, we have a very powerful integral constraint over the entire history of dust obscured star formation in the cosmic infrared background, as you know. And it looks kind of like they're comparable, the dust obscured and the unobscured. The estimate that I think you showed from Zavala or something, really just a kind of a guess, because they're using different star formation indicators to compare these different things. I think it might be a bit over optimistic. But anyway, the selling point, for PRIMA is we've got to really work this out. And obviously we know the dust obscured star formation is very, very important. I think that's a great story. Anyway.
Yeah. Thanks, Matt, for bringing that up. I also see Irini's hand up.
Yeah, go ahead, Irini.
Yeah, I was just also going to yes and, because there was conversations on the the peak for the obscured star formation, and to throw my hat in on how it's really going to be transformative on the obscured end. And I kind of touched on some of these points in the chat a little bit for AGN. Sorry, I missed the word there. So the issue is, even in our deepest X-ray surveys, especially at around cosmic noon, most of the inference we get at times when the X-rays are underestimating obscuration is by comparing to the closest we can get to in the mid-infrared, if possible. And when you do that, you see that the X-rays alone can significantly underestimate the total amount of X-ray luminosity coming from the AGN, which in turn will impact your black hole accretion rate densities and all your other markers of AGN power and growth. And so there's two things. We're really uncertain on, and this is what I spoke in the chat, on some of the lessons we learned at redshift 0, how they evolve to cosmic noon in a systematic way. Jed, you mentioned a point on this, and this is something I harp on a lot, is as galaxies get more clumpy and their covering fractions get larger, the chances of the AGN being obscured by ISM further from, the fiducial torus becomes higher at certain redshifts. And so you have an additional component to play for obscuring your AGN. And so how all this is going to shake out with what we found from redshift 0, which is if you select obscured AGN via WISE or IRAC or Spitzer spectroscopy, whatever, compare it to the X-ray, you get different types parameter space of the properties of the AGN. How that evolves, that's its own question. But
selection versus actual galaxy.
Because in order to do those plots you're showing, you need to say that we trust the completeness of the populations we're using to characterize those densities. And so we know there's issues, and JWST is great, but the lack of bona fide rest frame mid-infrared is really been a struggle to kind of do these apples to apples comparisons.
Yeah, and just to kind of leapfrog off of that, I think being able to do that for, individual galaxies, statistical samples is going to be fantastic. But one thing to note is what this really enables is sort of that like transitionary region science, right? Like not just like studying AGN as the most X-ray luminous quasars or studying AGN as the most obscured infrared bright kind of hot dog like things, right? Being able to use that really rich and unique mid-infrared data set to capture, the transition between the two to kind of reveal, if you will, sort of the whole transitionary demographics. It could be really powerful.
Awesome. We have time for more questions if anyone has them.
Arini and I could talk about
Go ahead,
this for a
Arini.
long
Yeah.
time.
I know we shouldn't. Me and Jen are very good friends, so this is a question. I'm curious if other people have thoughts on this. This is something I've been thinking about. So me and Jed as well have, especially these past couple of years, have had a lot of our focus on the early universe, a universe that's probably going to be a little difficult for PRIMA to super touch on, in the same system. Statistically robust way as it can do at slightly lower redshifts. But the question that I have is, how much has anyone thought about, when we're looking at what some of these early results coming out of JWST are, both in terms of the overall AGN number densities and the kind of early enrichments that are being predicted, and all of these other, it's happening earlier, it's happening more efficiently than predicted. And we use PRIMA to be the anchor down versus just, a lot of the science cases that I talk about, and I think others people have, are basically going from redshift 0 up to cosmic noon. But in the inverse, have you thought about what would be some like really great tests to do for PRIMA to kind of contextualize some of the results that we're getting at early times?
Yeah, thanks, Arini. And let me just harp on this figure on the right a little more, right? So you can envision a very early universe that seeds black holes extraordinarily efficiently at higher masses than we thought before. And then therefore to reach the redshift 0 relation, relatively speaking, you're allowing for much slower black hole growth, as opposed to less massive black hole seeds, which then require faster black hole growth to kind of catch up to the galaxies that we see today on this relation, right? And so that's exactly what this PRIMA PI science component is going to do, is to provide that anchor over the last like 10.5 billion years by measuring the black hole accretion rates and star formation rates, in these redshift bins, and then comparing them to these various simulations that kind of follow that path, right? And I think you can imagine, this x-axis is certainly going to be, or sorry, the y-axis that I'm showing here on the right panel, that's going to be, you can think about that as tracking also your initial conditions, right? So that initial extreme formation scenario, whether or not you need to, catch up to the galaxies and being like higher on this y-axis or not, and being lower. So certainly a part of this PI component.
All right, folks, if that's all the questions we have, thanks so much, Jed. This was an excellent talk.
Yeah, thanks, Betsy.
Just a reminder to everyone, tell folks who missed it, these are all posted on YouTube, so you'll be able to catch this later, and any of the other previous talks, like Arini's wonderful talk earlier, they're all available. So thanks again, and hopefully we'll see you next month.
Yeah, fantastic. Bye, y'all.
Thanks. Great talk. Thanks. Bye.
Thanks, Shad.
Great talk.
Good.